Diffusion and osmosis. The processes of diffusion and osmosis account for much of the passive movement of molecules at the cellular level. They are both types of passive transport, meaning no energy is required for the molecules to move into or out of the cell. Diffusion is the process by which molecules spread from areas of high concentration to areas of low concentration. Molecules will always move down the concentration gradient toward areas of lesser concentration. In the following video, we will witness the diffusion of food coloring through water. The water on the left is near boiling, very hot, and the water on the right is ice water, very cold. Notice the difference in the speed of diffusion as it relates to the temperature of the water. When the molecules are even throughout a space, it is called equilibrium. Given enough time, both the hot and cold water solutions reach equilibrium. Heat speeds up the movement of molecules, but at equilibrium, it is no longer a factor. This diagram shows the diffusion process from beginning through equilibrium. The cluster of molecules in the left image represent the drop of food coloring. The final image represents the evenly colored blue water in each glass. The next three images show the three types of solutions. Iso means the same, so an isotonic solution means the concentration of solute, maybe salt, is equal on both sides of the membrane. Water will move back and forth, but will not change the concentration on either side. In a hypertonic solution, hyper means more, so there are more solute molecules outside the cell. Water moves out of the cell. In plants, the cells lose water and shrink, causing wilting. In a hypotonic solution, where hypo means less, there are less solute molecules outside the cell. Water moves into the cell. In plants, this means the cells gain water and grow to become rigid or turgid. They do not burst because the cell wall prevents this. We will now do an experiment with osmosis. This experiment will show osmosis as it relates to plant cells. Cell membranes allow water and oxygen to move freely, but no other molecules. This means they are selectively permeable or semi-permeable. To recreate this experiment, you would need a potato, 2 flat containers, we used pie plates, water, salt, and a knife. To begin the experiment, slice the potato in half. Place a half cup of water in each container. Add 2 tablespoons of salt to the container on the left and stir the solution to dissolve the salt. Place 1/2 of the potato in each solution with the cut side down inside the solution. Leave this alone for a few hours. When we come back to the potatoes, we will examine them. The one in the water on the right, with no salt added, looks the same. It is rigid and has good color. The one on the left, in the salt solution, has shrunk and looks wilted. It is visibly smaller in size as the salt has caused water to leave the cells of the potato, thus shrinking the individual size of each cell. The salted side of the potato has lost water from its cell due to the salt solution reducing its size from its original healthy state. The cells have been dehydrated. The potato in salt is less than 1 5/8 inches across, while the potato that was in plain water is around 1 7/8 inches across. This means the saltwater potato lost approximately 13% of its size due to osmosis in a hypertonic solution. The loss of water to the cells has resulted in loss of cell wall turgidity, making the potato pliable, easy to bend between your fingers. The potato in water did not burst because the cell walls prevent this from happening. This shows how dehydration contributes to the wilting of plants. Without the semi-permeable membrane, all molecules would mix evenly and the level of solution would be the same on each side. In this diagram, in the potato experiment, salt was like the solute. Salt draws the water in its direction, or to help you remember, salt sucks. Equilibrium is reached in solution when either all molecules are distributed evenly, when there might be no preventative membrane, or when both sides of the membrane have reached the same solution concentration, when there is a presence of a semi-permeable membrane, preventing certain solutes from passing through freely.